All right, thank you. Hey guys, thank you for having me today. My name is Philippe Gläser from Technical University of Berlin, and you just heard the title of my talk. So let's get on it. First of all, let's talk about why polar lunar illumination might be more interesting than at other places in the solar system. Well, here, not to scale, obviously, we can see the sun and the moon. And keep in mind that the moon-Earth system is orbiting around the sun in the so-called ecliptic. And we can think of the solar rays hitting the lunar surface all in parallel fashion. So if you were to land on the equator, like all the Apollo missions did, you would expect to be in the sunlight for 14 days, followed by a night of 14 days. But if you were to land at the lunar poles, the situation is quite different. And we have a couple of axes at play here. So let's start. First, we have the normal of the ecliptic plane, which is shown here. And then we have the normal of the orbital plane, which is tilted by 5.1 degrees to the normal of the ecliptic plane. And the orbital plane, meaning the lunar orbital plane, is not lying perfectly in the ecliptic, but it is tilted by these 5.1 degrees. And the lunar rotational axis, on the other hand, is tilted by a total of 6.68 degrees within its own orbit. So that's called the lunar obliquity. And it turns out, though, that the lunar rotational axis is always tilted 1.5 degrees to the normal of the ecliptic plane, independent of the lunar precessional cycle and so on. So this is the so-called, has to do with the so-called Cassini state, for those who are interested in orbital dynamic. And it's exactly this angle, the 1.5 degrees here between the normal of the ecliptic plane and the lunar rotational axis, that is responsible for extreme illumination conditions at the poles. So if you want to imagine a deep crater, let's say located right at the lunar south pole, and we have all these parallel sun rays coming in. It's easy to see in that sketch that these sun rays will come in at about 90 degrees angle and will have no means to ever penetrate within deep craters. So we have a large area of crater interiors that will never see direct sunlight. And we denote them permanently shadowed regions, or short PSRs. I'm sure, I know you have already heard of them during this meeting. And the sun ray coming in might only be there to illuminate the upper parts of the crater walls. So just a thin part of the crater walls might be illuminated, but the larger parts of these craters will be in permanent shadow. And these craters, or these PSRs, were already promoted 60, 70 years ago. But now we have the means to actually pinpoint where they are and map them precisely. And here, I want to highlight one mission. It's called LRO, the Lunar Reconnaissance Orbiter. Maybe you're familiar with that mission. It is in orbit since 2009, and it's still ongoing. And one instrument on board called LOLA is of particular interest, at least to me. LOLA is the Lunar Orbital Laser Altimeter, and it can measure the lunar surface in 3D, like it measures a lot of points on the surface. And from these points, we can create so-called DTMs, digital terrain models. And one of these terrain models I show you here, this is a 400 by 400 kilometer DTM representation of the lunar topography with a resolution of 20 meters per pixel. And here at 0, 0, I show you the axis here in kilometers. At 0, 0 is where the South Pole is located. So we have the lunar topography at hand. So now we could go ahead and just say, okay, we're interested in, let's say, this subset of the DTM, which is show a zoom in right here. And again, at 0, 0 is the lunar South Pole, and it is located right on the rim of a large crater. And that crater is called Shackleton crater. You have probably also heard of it before. And here we have a beautiful ridge, which we usually denote connecting ridge. It connects to this crater over here, which is called the Gläser crater. So if we were to synthetically illuminate this part of the lunar surface, we take this DTM and put it in a computer program and illuminate it. You can already, you know that we probably need to take into account much more of the lunar topography, because mountains as far as 100, 200 kilometers away, like the Leibniz Plateau or Malapert Peak, they will obstruct the sunlight from hitting our surface patch here because of these grazing sunlight coming in, the high incidence angles of 90 degrees. So we need to put a lot of data into our programs to actually illuminate a rather, let's say, small 50 by 50 kilometer patch, just to keep in mind as background information. And quickly of how that is actually done. So we make use of a so-called horizon method, which is a very simple but powerful method. What it does, it technically just determines the horizon line that can be seen from an observer on the lunar surface. So imagine we place an observer in each pixel on the lunar surface in our DTM and determine the horizon line. And it's somehow similar to what the Apollo astronauts did. So here I show you a panoramic image. The astronauts had a camera mounted to their chest, and from time to time they would stand still and turn 360 degrees around their own axis and take a lot of pictures. And these pictures were stitched together to form a panoramic image. So you see here a 360 degrees panoramic view of that particular location where the astronaut was standing. And what we are interested in our program is only this horizon line. This line might be at different distances from the observer, but it is very crucial to determine for our algorithm. So an horizon line is made up of elevation versus azimuth. And that's all we need to calculate from our DTM that we have now, thanks to Lola. And it's very, very computational. But the good thing is we only have to do that once, because all of these profiles are time invariant. Unless a huge asteroid is striking the moon, these profiles will stay the same for hundreds and thousands of years. So we only have to calculate it once, and we can store it in a database. And then it's very straightforward and easy to derive illumination conditions and also Earth visibility. And it's done like this, just to show in a sketch. So at a certain point in time, we will just have to pull the azimuth and elevation of the solar disk and from the Earth and plug it into our horizon profiles at each pixel. And we can then straightforward determine, okay, here the sun, the solar disk is visible, like at least parts of it, let's say 10% of the solar disk is visible, but yes, we can report some illumination. And the Earth is completely above the horizon, so we have means to talk home to Earth, and we can also determine which part of Earth, or more specifically, which telescopes are visible at that certain point in time. So with these horizon profiles, we have now all the tools at hand to create large scale and long time periods of illumination, or look into them. And some numbers for you to take home. For an observer at the lunar pole would see the solar disk in a size of about 1/2 degree, whereas Earth would be about 1 degree. And the apparent movement of the solar disk above and below the horizon will be about 1.5 degrees, which is exactly that tilt of the lunar rotational axis with respect to the ecliptic. The period will be about 1 year. Earth itself will have an apparent movement of plus minus 6.68 degrees, which is the lunar obliquity. So it is a much larger movement than the one you see from the solar disk. And the period is very short in comparison at 27 days. So that's what you expect as an observer, or as a rover landing at the lunar poles. Now that we have all these horizon profiles, we can go ahead and create the so-called average illumination maps that I show over here. The left-hand side, for reference, I show you the topography of our region of interest again. And what we've done now is we've said, okay, create horizon profiles for an observer at 0 meters. So for each pixel in the DTM, we put an observer thin as a paper on the lunar surface and determine the horizon profiles. Then every hour and over a time period of 20 years, for each pixel, we determine, can you see the sun or can you not see the sun? Or can you see parts of it? And we summed up all of these numbers and averaged them and put them in a plot where we color code the resulting value. And what you can see now are values between 0 and more or less 80%. So from blue to red. And what sticks out is that there are large blue areas. For instance, the interior of Shackleton crater. And I can tell you it's not 10%, it's not 5%. These blue colors here indicate 0%. So these are the means how we find PSRs now, because here we can state that over a period of 20 years, and we've checked every hour, exactly 0 times there was any sun ray hitting this large field here. So this is a very large PSR right at the lunar South Pole. And on the other hand, it turns out that the most illuminated spot is also located at Shackleton crater here on the crater rim. I circled it in with this black circle. So it's somewhere here right on the rim, and it amounts to 85.5% of illumination. So 85.5% of the 20-year time period, that point location was in the sun. Maybe the whole solar disk was visible or parts of it. You can't see that in that kind of number. But what you know is that for a majority of the time, you do at least see the sun a little bit. So that's a very, very, very high number. And now we're thinking, okay, if we land on the moon, we're not going to be thin as a paper and lying on the surface. So let's think of a rover, a structure that is typically, let's say, 2 meters above the ground. And we have a solar panel at 2 meters above ground. Does that make any difference? And it turns out that the difference is significant. Just by going up 2 meters above the surface, you can see these red areas here becoming way more pronounced, meaning we have much larger areas that receive 80% or more of the illumination of our 20-year time period. But also, we find that the most illuminated spot is not at Shackleton crater anymore, but it jumps over here, which is located on the connecting ridge, on this topographic high, on this little mountain here. And we find a staggering 92% in the sun. So just by going up 2 meters, on average, you can be in the sunlight for over 90%. That's good news. Now we're thinking, okay, let's look at 10, 20, whatever meters. Maybe we find a point of eternal light, which people were really interested in. If you can go up 100 meters or so and you find a location where you have a solar panel at 100 meters and you have 100% sunlight, meaning you can create endless energy for your mission timeline as long as you want. But going up to 10 meters, we only find 95.6%. At 20 meters, 96, and at 100 meters, 97. So we played that game up to 2 kilometers, and I can tell you we did not find a point of eternal light anywhere close to the lunar surface, at least not at a height that could be anywhere feasible in the near distant future. So to summarize here, we have height above the surface versus average illumination. We find that at the surface, we have 85%, and just by going up 2 meters, we already find a spot that on average has 92%. And I have to say on average, because average means we include lunar South Pole winter and lunar South Pole summer. So obviously in the winter, you have less illumination than in the summer, but it's an average value. So including all the winter times as well, we end up with 92% already. And then going up another 8 meters from 2 to 10, we only add 3.6%. So you can already see that the gain, there is still a gain, but it's not as much anymore. And then going to 20 meters, it almost stays the same. But I think that is good news, because structures from 2 to 20 meters, let's say, it's something that we could envision today. 100 meters or more might not be feasible, but the most gain is exactly in that area. So it is somewhere close to the lunar surface and can be harvested by a future mission. But these average maps just tell you so much. If you wanted to land at a certain spot, you want to know exactly what is the illumination over my mission period. I don't really care about average values. I really want to know what is my illumination when I land there. So we just picked, not randomly, but we picked a site here at the connecting ridge that we wanted to look into more detail. So I show you zoom in the topography right here. You see it's a little mountain. It looks like there is snow, but that's just the color code I chose. So this is the highest spot on that mountain. And if we derive illumination at 2 meters above ground, we find large areas shown here in black that have 70% and more illumination during our chosen mission timeline, which is a 2 months period. And this point in particular sticks out. And now, if you design a mission, you can create these kind of plots. This is a plot showing you the visible solar disk fraction over your mission timeline. So no average values. This shows you the instantaneous illumination at a certain time. So let's say we would have landed in December 2022, and our mission was until February of this year. That would have been the visible solar disk fraction over time when landing right here at the spot. So you start out with the solar disk being completely visible. It just drops down maybe to 90, comes back fully again. So you have the full solar disk available to create energy, and then it drops down to 0 for 1.5 days, 35 hours, before it comes up again for 28 days straight. So these plots are very important, because can you actually survive 35 hours without producing electricity? That's one question. The other question is, it will get really cold in these 1.5 days. Can you survive that as well? Nevertheless, if you choose a specific mission time, you choose obviously summer or winter, whatever you're looking for. And here we chose southern summer. So we find almost 96% of illumination for our mission timeline right here. So almost constant illumination. And the same plot can be done for Earth communication. So if you were to land here, this would be your Earth communication plot. Here I show you visible stations. That would be ISA S-track and the Deep Space Network. In total, there are 22 antennas. And can you actually talk home? And it turns out that for 15.5 days, you have between 4 and 16 antennas that you can like communicate with, send your data down. But then there is an 11-day time period where you cannot talk home. And so can you store your data on board 11 days before you download them again? Or can you not? So this plot is also very crucial for mission design. Like if you have to rely on direct Earth communication, unless you have another satellite in orbit that you can use. What I want to stress here is, although the landing site we chose is on the far side of the moon, just slightly, but it is on the far side, we still have Earth communication of about 50% of the time. And intuitively, one would say, once you go to the far side, you're doomed. You can't talk home. But that's not entirely true, as long as you don't go too far over into the far side. And that has to do with the 6.68 degrees apparent movement of the Earth above and below the horizon due to your obliquity of the lunar orbit. So we have possibilities to talk home, even landing on the far side. Now we've covered illumination. Let's switch over to thermal conditions. So far we were talking about illumination, sunlight coming in. We can also think of insolation, which is not, is there sun or is there no sun, but it's more like how much watts per square meters are actually received here. Think of the solar constant, which at the moon is about 1300 watts per square meters. And it makes a difference if that spot that we're looking at is actually tilted towards the sun, or if it's not tilted towards the sun. If it is, you can think of a more efficient heat up, because more watts per square meters can receive. So you lower the incidence angle by tilting that surface towards the sun. And that happens for here with this crater wall, which is in this sketch shown to be tilted towards the sun. But also we have to now look into the reflected light, because parts of that incoming light will be reflected right back into space, which is tied to the albedo of the moon. The albedo is very low, but it's still reflecting light back to space. That spot will heat up and will also conduct heat into the subsurface, which is depth and temperature dependent. And also from the internal And from the lunar interior, we have internal heating due to radioactive decay. So we have to take that into account as well. The subsurface itself will be made up of different densities, which are depth dependent, and heat capacities, which are temperature dependent. So that makes the whole thing a little complicated. Also, that spot will heat up and radiate into space, which is emissivity and temperature dependent. And last, and crucial for our undertaking at LGWA, is scattered light will also be received at this spot. Think of the illuminated terrain around here. It scatters sunlight also to this spot. Also through, let's say, multiple scattering, sunlight will be received here. Thermal radiation will come from all of the terrain surrounded this spot, from the illuminated and the not illuminated part, because all of the terrain is warm, like meaning above 0 Kelvin. So it will radiate also some additional heat over here. So we have to take into account all of these parameters. And once we do it, I spare you the details, we end up with something like this. Up here, I show you average temperatures. On the bottom, I show you maximum temperatures. And again, our study region, the topography for reference is shown here. This middle panel now shows you the average insolation scale from 0 to 1. So it's not illumination, but insolation. Like how much watts per square meters are received at each pixel on average. And white pixels mean a lot of watts per square meters, dark pixels or black pixels mean 0. And as we know, the inner part of Shackleton is a PSR, so we also end up with 0 watts per square meters coming from the sunlight, from that direct sunlight. But what you can see here, interestingly, is that part of the inner crater wall of Shackleton seems to be quite insulated. There are like high values on this crater wall and almost nothing on this crater wall when we look at average values. And that has to do with the fact that this crater wall is facing towards the equator. So it is also facing more or less towards the sun more efficiently than this part of the crater wall, which is facing towards the pole, which is right here. So the equator-facing crater walls are more efficiently heated than the pole-facing crater walls. And that is reflected in the temperature maps as well. So here I show you the average temperature maps of our study region. And if you look closely, I hope you can see it, within the PSR, this inner crater wall, although it is a PSR, has a higher average temperature than this part of the crater wall. And that might all be a little bit confusing, what I'm saying here, but what I want to stress is that PSRs don't have a homogeneous temperature. They have also variations within, and that has to do not only, but also with the location of the pole and equator-facing crater walls. And it becomes even more evident looking at the maximum temperature maps. So as you can see, the inner crater walls receive the most insolation of our study regions. So because they're up to 30, 40 degrees slopes here, so you lower the incidence angle and you increase the insolation. And that's why the inner crater walls heat up to 300, 350 Kelvin. Whereas then you have this sharp boundary into the PSR where you find at maximum 100 or 50 or maybe even a little less than 50 Kelvin. But you still have variation within PSRs. And with that, I want to go to our landing site again, the fictitious potential landing site we're looking at. And let's now focus on this little crater here. It's actually a little PSR, a small one, but it's a PSR. And here I zoomed in the topography a little bit more to show you the profile of that crater. And if we blow it up a little bit, this is the profile of this little crater, which is a PSR, at least parts of it. And one of the crater rims raises 20 meters above the crater floor, and the other one 40 meters above the crater floor. Keep in mind that this is not, this is an exaggerated scale here. So it's a very, you can see it here, it's a very little bump here only. And the crater diameter is about 200, 250 meters, which might be just enough for the LGWA. And with Professor Harms, we were already discussing an idea of, okay.
You have 5 minutes.
Oh, perfectly. What if we were to land here at the crater floor, making use of the PSR and the cold temperatures, and also make use of the illumination, which happens, let's say, out here. So we have a solar panel mounted at a certain altitude, and we harvest the extreme illumination conditions as well as the cold temperatures. So make use of the both extremes that we found at the poles. And it turns out that within this little crater, we found a position here marked in X, which at a mission timeline of 3 months, okay, this is in 2004, but it might as well be 2034. It doesn't really matter. We find insolation of 0%, like no watts per square meters, nothing. So we are not receiving any sunlight. That's what we want. What we do find, though, is that we have from the surrounding terrain, we have thermal radiation coming in at around half a watt per square meter, and scattered light adding another 0.1 watts per square meters. We also looked into Earth radiation, but here the thermal radiation and scattered light coming from Earth is a magnitude, an order of magnitude smaller, and we might not even have to consider this. But in our resulting temperature line at the PSR, at the landing spot, we can see there is some sort of variation, which perfectly basically resembles the thermal radiation coming from the surrounding lunar terrain. So we do have amplitudes of 10 Kelvin maybe, and on average, we have maybe 50 or 60 Kelvin on our landing spot. But we could think of burying the instruments 1 centimeter only, and that line would become very flat and lower because the lunar regolith is a perfect insulator. So our biggest enemy, talking about temperature, is the thermal radiation from the lunar terrain, and we have to mitigate that. On the other hand, that solar panel that we mount here at 15 meters above ground would indeed have more than 50% of the time illumination and could deliver electricity or power to our instruments down here. Of course, this is a very preliminary study, but it shows that small-scale PSRs might be a solution for the problem. And so I want to conclude here with a couple points that we can derive illumination conditions over large timescales and also high resolution. High resolution is a relative term, but let's say at 20, maybe a little bit better meters per pixel. And we can do the same for thermal conditions for the lunar surface, but also for the subsurface, which might be interesting if we have some mechanism to bury the instrument so we can check the temperatures there as well. And that enables us to also create detailed maps for the small-scale PSRs with respect to illumination and temperature. And as we have seen, also important to observer height. And the last bullet point is Earth visibility, which I think oftentimes is neglected, but it's kind of important to know if and when you can talk home to Earth. So with that, I say thank you. And if you have questions, I'm here.